Okay, thank you very much. So you can hear me okay? And Tromsø? Yeah? Okay. So what we're interested in here is that we want to solve the Schrödinger equation, of course. And what we do here is that we restrict wave functions that are L2, but also have finite kinetic energy. So this is the Sobolev space of wave function, and here it is denoted H1, and then with the subscript n to indicate that it's n electrons that we're interested in here. I will use this notation for the L2 inner product on the full n electron space. And then, of course, this H here models this n electrons. And there's, of course, some criteria on this Hamiltonian, but the technical ones I will skip and just say that the main assumption here is that we have a non-degenerate ground state that will be denoted psi subscript star. And that means that we have a spectral gap between the ground state energy and the rest of the spectrum. So in the analysis that I will be talking about here today, we will make use of a Slater basis, and we construct it in the following usual way. So we look first at a basis for the one electron space. So here we have the Sobolev space, so L2 functions with finite kinetic energy for one electron. And we split it into one part, that's the occupied space. So here we have n one electron function or orbitals, where we put one for each electron. And then, of course, these electrons can be excited to virtual one electrons or function or orbitals, which is this space here. And then we want the collection of those functions denoted here to be a basis for this one particle Sobolev space. And next, we define a multi-index. So we have here a sequence of n integers in increasing order, and then we say that a determinant phi mu is simply the determinant constructed with those one electron functions indicated by the multi-index mu. And in particular, if we put the n first one electron functions in the construction of the determinant, that is, we make use of this set here, then we get something that we call psi naught, and that's the reference determinant. And from all these determinants, we can build up or span our Sobolev space H1, and we make use of two different multi-index sets. So one is this M, and that contains all the excited determinants. And M index 0, M naught, contains also the reference determinant phi naught. So that's just notation, because it will become obvious later when I talk about excitation operators why you want to split this into two different multi-index sets. Okay, so let us first look at the couple cluster approach before I talk more about our work on the extended couple cluster. So let's start with the Schrödinger equation again, and here we have the weak formulation. So we want to find solution psi such that this hold, and it should hold for the ground state energy E subscript star here. But we have just constructed a Slater basis, so this can also be formulated in this way. So for all mu, and then we have the full multi-index set, so it contains all determinants that make up our Hilbert space. So this This is the weak formulation using the Slater determinant, the Slater basis of Slater determinants. Okay, so the first step, we assume this intermediate normalization. So when we look at the psi here, we say, okay, it has weight 1 in this reference determinant, phi naught, and then some correction that's in the orthogonal complement of this reference determinant phi naught. And then we can write the Schrödinger equation like this. So now it's all about determining this correction, psi perpendicular, or what we can call it. Okay, but this now sets the frames for next step. So now we can introduce cluster operators. So here we have a sequence of real numbers indexed by this multi-index. And this multi-index set is now M, not M naught, so it's only excitation, so to speak. And then we define a cluster operator T, simply as this possibly infinite sum here over the multi-index mu with this weight, with these cluster amplitudes, and these excitation operators. And this excitation operator we define like this. So acting on the reference determinant, it creates the determinant determined by the subscript here. So this multi-index mu determines what one electron function builds up this determinant phi mu. And of course we could do this more in general. Look how an excitation operator acts on a general wave function, but then it quickly becomes much more complicated, and I won't deal with that here, so we will skip this, but I can just, as an example, if we look at this thing here, for instance, if we have a 2-electron system, then we have to restrict. So in that case, this phi naught is, let's say it has chi1 and chi2 in the occupied space. So then this one needs to be a single excitation, maybe promoting chi1, and then this one has to be another single excitation promoting chi2. So then this one only survives if these excitation operators are singly exciting the reference determinant. And all in all, we get something that is doubly excited. But for now, I just use this one. This will be enough for the discussion here. And this is much more simple to see, okay, this excitation operator with the multi-index mu, then it promotes this psi 0 to phi mu. Okay, so returning to the, returning to this in step 1, what we have here. We can write this phi 0 plus this perpendicular correction as, and here we make use of the basis expansion, because we know that this is something that can be expanded by determinants only in this multi-index set M. Okay, but now we recall that this phi mu can be written as this x mu acting on phi naught, so that then we get this, what we have here, if we just define this S like this. But this is how we define a cluster operator. So now we are with this equation we have here. So solving the Schrödinger equation is now about determining the cluster amplitudes in this cluster operator S here. So then we define a space where this cluster amplitudes lives. And then we just say, okay, a cluster amplitude that is square summable over the index set, multi-index set M. It is in this space capital V if this norm here is finite. And this norm is simply defined as we look at the corresponding cluster operator that is defined by these cluster amplitudes, and then we say, okay, this one needs to be L2 and have finite kinetic energy. So it is in this Sobolev space. Okay. So the next step is now we want to reparameterize this 1 plus or identity plus S into an exponential ansatz. So then we make use of this theorem here. It says that if the cluster amplitude is in this space, capital V, that we just defined, then the corresponding cluster operator is a bounded operator acting on this Sobolev space of L2 function with finite kinetic energy. And moreover, the exponential is a bijection between this set here and this set here. So that means that we can find a t such that the exponential of t is exactly identity plus s. So returning to the Schrödinger equation, we can now write it like this. And now we make, so here we have the couple cluster theory, but the next step to make the equations that we need to deal with later more easy, we make use of that this operator here is surjective, so we can put this operator here in the bra and then move it and then rearrange the equation we have here to get something that looks like this. Okay, so this is now the weak formulation of the Schrödinger equation through this CI that we had a slide before, and now after this exponential parametrization we have the coupled cluster formulation. And what we do now is that we split this multi-index or the multi-index set M into the one that deals with the reference determinant, and then the rest that we just called M. So we define this coupled cluster function F simply as this, what we have here, restricted to multi-index in M, so without the 0. So then we have this one here, and then we define the coupled cluster energy simply by putting the remaining index, the 0 index, in the left-hand side here. Because if we can find a t star, small letter t star, that is 0, then when we plug this t star into the energy expression, we must have the ground state energy from this expression here. So, and this is summarized in this theorem. So this psi star, this solves the weak formulation of the Schrödinger equation if and only if these cluster amplitudes is a root of the coupled cluster equation, and the number E star here is comes from the coupled cluster energy functional. Okay, so that's the exact formulation. So now let's look at the truncations and see what can happen. So of course, in practice, we don't have this B virtual, as I call it, the set of virtual orbitals is not a complete basis. So we have a finite set of this chi A. And that means that the Slater determinants, they won't span the whole Sobolev space. So we look at the coupled cluster function for a finite set of index, so a vector. And then solving that equation gives maybe something else than T star. Let's call it T index capital D. And when we plug it into the coupled cluster energy functional, we get some energy that I denote E index capital D. So that's one way we can have truncate, but we can also truncate because we might not be able to consider the full excitation level in the cluster operators. So if we have many electrons, we might keep the single, doubles, etc. up to some n prime folded excitation where this n prime is less than the actual number of electrons. So that's denoted here by this prime. So then we solve this coupled cluster equation, and let's say we get a root T index small d, and when we plug it in, we get some other energy. So this is the truncation scheme that we have. And of course, this energy here does not need to be an upper bound to the exact energy. Okay, so what can we then say about the energy? So in the work of Rohwedder and Schneider that me and Simon have looked into, they have actually managed to get this error estimate by looking at the Lagrange formulation of couple clusters. So you minimize the energy, the couple cluster energy functional, with a set of constraints. That is the couple cluster function in this case. So this is a bit tricky to do because you have an optimization problem with the constraint. So then you have to qualify the constraint. So that they managed to do and actually show that this is you have this kind of energy estimate. So this is the cluster amplitudes, and also you have this Z here, which is the Lagrange multipliers. Okay, but now we will move on to the extended couple cluster theory in this bivariational formulation, and then we will see that we will get more or less the same, but then these Lagrangian multipliers instead is another set of cluster amplitudes used to parametricize a wave function pair. So let's look at the extended couple cluster. So we define this bivariational energy quotient. So it is the usual, in a way, the usual Rayleigh-Ritz quotient, but we here treat the bra and the ket as truly independent variables. So we put a prime here to note that it's not the same as psi. And Arponen, he studied this and he made a smart choice to get rid of the denominator here. So that's what is done here. And then we define this submanifold of the full product Sobolev space, because here we want to parameterize two sets of wave function. And here we have nothing but this intermediate normalization of psi. So the weight of psi in the reference determinant phi naught is 1. But here is another criteria that makes the equations more feasible. But as we see here, that means that the parameterization of this tilde psi includes two sets of cluster operators or cluster amplitudes. So this is the parameterization of this wave function pair. Here we have the similar as in couple cluster, but here we also parameterize this psi tilde with a lambda. So note here that lambda is an excitation, a cluster operator of excitation operators. And with this L2 adjoint dagger, we get de-excitations. So the most important thing here is that this map from these cluster amplitudes to this double space of a wave function is smooth. So we can, with this reparametrization, plug it into the bivariational energy quotient and get an energy functional that is smooth in these cluster amplitudes, and we can take derivatives of this here. So that is what we will do next. So here we just a theorem that states that we seek the stationary points of this couple cluster extended couple cluster energy functional, because then we get the solution to the Schrödinger equation. And here we have the derivatives of this energy functional. So here we have the derivative with respect to lambda, and here with respect to t, and we just denote them f and f tilde, and defined this two-component big capital F in this way. So we can see here, if we plug in lambda equal to 0, we have the usual couple cluster function here. But now we also have a lambda. And here we have a slightly more difficult expression. So anyway, we plug it in here, and note that it's not the gradient, because we have flipped the order, but it's something that's very similar to the gradient. So if the gradient is 0, then f is 0, and vice versa. Okay, so now we want to look at solutions to this capital F equal to 0 on this double space of cluster amplitudes. So it's very similar to the couple cluster approach, but we just have a double set of cluster amplitudes and double the dimension, so to speak, for this extended couple cluster function. Okay, so the theory of in Rohwedder or Schneider's analysis, they use these two properties for F, and that is what we want to use for our capital F. So we want to establish a Lipschitz continuity and this local strong monotonicity, also locally. So let's look at those two criteria. So first, let me talk a little about this local Lipschitz criteria. So here is just the definition applied to this situation with the F we have here and with the amplitudes, the double space of amplitudes. So this is the criteria. We take difference in F, then we must be able to estimate it from above with some constant L, the Lipschitz constant, and then the difference, the norm of the difference in the amplitudes. But this we have because our extended couple cluster function, capital F, is just it's just the flip gradient of the energy. So this gives this Lipschitz constants in terms of the Hessian. So let's just look at a simple example here for local Lipschitz. So for instance, let's take this function here on the real line, x squared. Then this one, if you plug it into the definition and just make use of the conjugate rule, you can see you can estimate the Lipschitz constant like this. But this is nothing but the derivative. So that's what we do here, more or less. We just take the derivative, and that in this case is the second derivative of the energy. And here I just included something that's not Lipschitz. So this function here is not Lipschitz around the origin. So that's what's demonstrated here. Okay. So let's move on to this locally strongly monotone condition. So here is just the definition again. This is the criteria to have strong monotonicity. So here we have just the dual pairing of the inner product. In this case, it's an infinite series. Anyway, here an example of a function that's strongly monotone. You can, if we just plug it in, and then this is nothing, just the usual product on R, and then we see that in this case it's strongly monotone, and we can take this gamma to be this constant here. And this function is also strongly monotone, but here we might limit the interval. So if you just think of the shape of sinus on this interval, you can get a feel of what it means for this function to be strongly monotone. Okay. So the local Lipschitz condition we have directly from just taking the derivative of the energy. But to obtain this locally strong monotonicity, then we have formulated two sets of different assumptions. So to obtain this property, we either have to assume that the reference determinant, that's a good approximation to the exact solution, so that this correction here is sufficiently small. And also that there is a spectral gap. And what this means, spectral gap, and that this phi naught is sufficiently good, that means that this spectral gap also, I mean, this one and this one are more or less the same, so then we can formulate sort of a gap condition or a coercivity on this space here. So then that is what we use to prove the monotonicity and get this gamma. So gamma is closely related to this gamma star here. Either we can look at this assumption, so we split the Hamiltonian, and here now F is not the extended couple cluster function, it's the Fock operator, so I put the operator hat here to distinguish them. Anyway, if we do this splitting, then we have to assume that this fluctuation potential W here is sufficiently small. And in this case, this phi naught, the reference determinant, that's nothing but the first eigenvector to this Fock operator. And here we also need to assume a HOMO-LUMO gap for this Fock operator that in a way is big enough compared to the smallness of the fluctuation potential in a way. Okay, so let's look at let's look at error estimates in the extended coupled cluster theory. So we recall that we have two sets of truncations. So here I just put a prime on this virtual basis, or it's not a basis anymore, but a set of functions. So that's one way we have truncations, and also this excitation level of the cluster operator. And now we describe this. So we have this amplitude space capital V, and we describe any truncation, be it this or be it this, just by reducing the space of this amplitude space, and we put an index D. And then we let this be a basis of this finite dimensional subspace, so the truncated capital V in index D. And then we want to solve this extended coupled cluster function, so capital F equals 0, on this doubly amplitude space that is now truncated. So what we can do is that we look at solution of this form. So we first write it as a minimizing pair. So, and this is a minimizing pair in this sense. So this T index M, lambda index M, is the closest point in this truncated space to the exact solution. And here we add something that corrects this. So we allow some indeterminate coefficients that in terms of the basis on this truncated space. Okay, and then we have this this theorem. So if the distance between the truncated space and the exact solution is sufficiently small, so that's measured in this way. So this is the distance between the closest point. So that's what we had here. So this is the closest point to between the exact solution and the truncated space. So if that's less or equal to this gamma is the monotonicity constant, and L is the Lipschitz constant of this extended coupled cluster function F, and delta is some radius for which we have this Lipschitz and monotonicity on a ball with that radius around. Oh, sorry, here's a misprint. There should be a lambda. Apologize for that. It's a T star lambda star. Okay, but if this holds, then we have a unique solution. So in this a truncated solution that's unique on the truncated space, and also not outside the ball, for which we have the Lipschitz and strong monotonicity. And moreover, we have this estimate between the exact solution and the truncated solution. So again, given by these constants from monotonicity and Lipschitz continuity. And this here goes to 0, of course, as the truncations or the truncated space approach the full space. Okay, so since we have the bivariational formulation, we know that the solution, the exact solution, is a point for which the gradient is 0. So if we Taylor expand the energy, we get directly to second order. So that we used. So here we have a more direct or more simple approach to obtain error estimates. So we just we just Taylor expand, and then either under this assumption for which we have the strong monotonicity, we obtain an error estimate of this form. So here it's very similar to the error estimate you have in coupled cluster, but instead of the Lagrange multipliers, this extra set of cluster amplitudes takes the place of those Lagrangian multiplier. So we have it like this. Or if we want to, we can express this in terms of the distance between the truncated manifold. So here is simply, this was the map from cluster amplitudes to the wave function pair. So we take truncated cluster amplitudes, then we get a truncated wave function space, and then we can estimate the energy difference in this way. So in parallel. So okay. So to have a short summary. So what me and Simon, what we have done is that we have continued the work of Rohwedder and Schneider to study the extended coupled cluster theory. So we have a preprint available on Archive. And so what we've done is that using this bivariational formulation and then continue the analysis and study this capital F and show that it also has this monotonicity property. We have studied the existence and uniqueness and also this error estimate for truncated version of the equations. So that was a short summary of the work. Okay, thank you very much.
Thank you, André.
Yeah.
Questions? Sigurd?
Yes. On the last slide where you show the error estimates.
Yes.
So I know the answer, but I think that it could be enlightening for the audience. So this theorem gives you the existence of an error estimate for the discrete extended coupled cluster ground state energy.
Yes.
Right? So what is the significance of this result when you compare in the light of, okay, so we have studied extended coupled cluster theory, which is not the standard coupled cluster theory, but what happens when you compare this to standard coupled cluster theory and to variational methods like full CI, etc.?
Okay, so compared to the usual coupled cluster approach or theory, you see that it's you have the same as in coupled cluster, but you just, instead of this lambda, you have that in the extended coupled cluster theory that are cluster amplitudes, you have these Lagrangian multipliers. But of course, if you compare the Lagrangian with the bivariational energy, you see that the Lagrangian multipliers is in a way like linear approximations to these cluster amplitudes here. So that's the I mean, it's not it's very in parallel to the coupled cluster theory and what you might expect to have. But and then I don't know if that was the what you were fishing for, or
well, yeah,
yeah, but
my point is just for a variational method.
Yeah.
It's very common to say that when you have a variational method, you have a quadratic error estimate.
Yes.
Etc. And this is precisely what we have here.
Yeah.
For a method which is non-variational in.
Yeah, that's true. So okay, so it's non-variational in the sense that you don't have this variational principle of upper bound of the energy, but it is variational in the sense that it's stationary. The bivariational energy is stationary. That's why you can use the Taylor expanding. And the same with the Lagrange formulation of the usual coupled cluster. It's also variational since it's you set the variation of the Lagrangian to 0. But of course there you have no easy way to obtain this. Let me see the results here. This is not obvious in this case. I mean, here you have to. I think if I'm not remembering wrong, when they qualify the constraints, they use the Lax-Milgram theorem, I think, to obtain this. So it's a little less trivial than just Taylor expanding.
More questions?
So I just have a question.
Yes.
Like, is this formulation tested on the numbers? Like the error estimate is tested against some molecules or like some calculations?
What you for couple cluster you mean?
Oh yeah, for like all this error estimate or this.
Yeah. So I think I know that in their in one of these articles, Rover Schneider, they quote some articles that because this was believed to be true. I think they say before they proved it. So sure, and also that's something that we are working on also to connect this to actual calculations in this particular setup in a Slater basis. When you have fixed the Slater basis, and then you just let me see, sorry, here, and then you just add or remove one more of these, and then you see how the energy estimates holds and compares. Yeah.
More questions? From Oslo? I see no hands from Oslo. What about Tromsø? Yeah,
Ingal, there's one from Ingal. Do you see him?
Yes?
Yeah, I think I have a comment more than question. To be honest, I was lost from the beginning of your talk. I think that there are 3 reasons for me to lost. First,
Okay.
I feel your talk is very logical, and in any step I become lost, then I totally lost. I cannot follow you until the final conclusion. And also, you have so many notations, and if there's one notation I don't understand its meaning, and also when you change the next few slides, if you still use you cite some notation you already defined, then I also lost.
Okay.
And also, for example, on your slide 9, yeah, the second equation, I totally don't understand its meaning. It's it's a product of 2 space or 2 set. It's Hn1, and then there's a column. That I don't understand.
Okay.
I know
So
the first column equal is definition notation, but others I don't know.
Yeah. So this just means that this one goes there, and this one goes there. Okay, and this column means that whatever you have here must satisfy whatever stands here.
Okay, but
Yeah.
I don't understand its meaning
No.
if you don't explain to me. And my third reason is I really feel it's hard for me to understand all the notations in such a short time. Is it possible for you to extract some take-home message, some sentence, or some words from your formula work? And if
Okay.
you can provide some figures or tables, that will help me.
Oh, but
And
I don't
also,
have any.
for instance,
I don't have any figures and tables to provide you. I'm sorry. This is purely
also like,
theoretical.
Also, when you describe, you have several steps to step 1, step 2, until step 5 to get the couple cluster truncation or something. All these are formula. Is it possible to change some figure or something? And also
Yeah, okay.
your summary. Summary
Yeah.
I still don't get your point from your summary.
Okay.
The final slide.
Yeah.
Yeah. And
Yeah, that was more of a comment than a question. I agree with you.
My background is I want to convert the formula into code to run on computer program. So when I listen to your slides, I always have such question. Okay, you have a nice, beautiful formula, but can you, from your formula, how can we use your formula? Can we program your formula? Can we code your formula? Yeah.
I mean, I don't know what to, I don't know what to answer to that. Okay, so thank you very much for your feedback. Thank you very much. Yeah.
Are there more questions or comments?
No more comments. No more comments.
Yeah, my question, I have a question. So how far would it be from there to a possible implementation? I mean, I rephrase his comment into a question.
That's not on my table, I'm afraid, to implement it. So yeah, I think that there are some implementation, aren't there, Simon? Yeah.
The reason why we studied this method is, I freely admit that the motivation was not to study a very, very popular and extremely useful computational technique in quantum chemistry. Extended coupled cluster theory is not something which is routinely run by computational scientists, because it's very complicated to implement, and I guess that there are many opportunities for mistakes because the equations are very complicated. But it shows, the point is that it sheds light on the structure of also traditional coupled cluster theory. That means, well, I mean standard coupled cluster theory. In this ERC project that I run, in which André is a postdoc, they're trying to find out more about the bivariational principle from a mathematical point of view, and this was the first sort of big proof of concept analysis showing that the bivariational principle actually is a rigorous and useful way to obtain new types of quantum chemical computational techniques. That's this analysis is it is complicated, but that's how it goes with state-of-the-art methods.
Tromsø, could you hear the reply from Simon?
Yeah, more or less, yes. Yeah, I heard it. I mean, I think it is proof. I mean, you have to start somewhere. And my question was more like informative, meaning it was not trying to dispute the quality of the work. It was like, I just want to know how far one is from this kind of formulation to an implementation. So, yeah, that's totally fine. Okay.
I'm just saying that we are not aiming to implement it either, but we are aiming to implement other methods that are more that have not been explored before.
Okay.
Thanks.
Thank you. And then there is another question from Oslo.
Just a quick comment on it.
No more questions?
I heard about one guy trying to do an osmotic implementation of ECCSD. I think he ended up with 25,000 terms.
Yeah. Did you hear, Rolf, you had a comment that this implementation or this type of implementation of ECCSD ended up with 25,000 terms to be coded.
Yeah, well, the coding was also...
I hope it was automatic generation.
Yeah, I guess.
I see. So it's not like a factor 2 slower. It's a bit more.
Well, but then you gain accuracy. So
it's a trade-off versus speed and accuracy, Simon says. Yeah. Okay. So any more questions, comments? No?
No.
If not, let's thank the speaker again.
Thank you very much.
And have a nice week.